Right, great. I realized this morning that I didn't announce the lecture as I usually do. I hope that you still all remembered that there is a lecture today. I'll try to make sure that I announce them earlier, but yeah, it's always the same thing. The only difference is the chat. Okay, so Lab 4 is still out. You still have 1 week to finish it. Hopefully it's going ahead well. I don't hear too many things from TAs in terms of lab attendance, and so I'm assuming you're just working on it and that there are no problems. Midterm is coming. Today we're gonna finish how to determine that the language is LL1. This will be on the midterm. This is the last topic that will be on the midterm from the topics that we're covering. So anything after this lecture will not be in the midterm, but will only be on the final. Midterm, there were a few questions in case it's not clear. I'm just taking the whole week off, treating it kind of like a normal midterm week. So there are no lectures. The midterm will be out on Monday, and it will be available for the week. The midterm will be 75 minutes, plus extra time because it's online, plus extra time afterwards so that you can submit anything that you need to scan and all of these things, so that you don't have to worry about scanning and then also working on problems. There are questions, sample questions or study questions for midterm that's been released in our PDF repository. There's going to be a midterm lecture where I'll just work over some problems similar to the ones that you would see in those questions. If you have any specific questions, send me requests, like what you'd like me to go over, if there are such things. This is going to happen next Friday. Okay, so with all of this, let's get to today's lecture. So we still have the same slides of grammar is LL1. We're going to do a brief review of where we are, and then finish this up. And if we have time, we'll go through a more detailed example than the one in the slides. What are we doing? We need looking at the method how to determine whether a given grammar is LL1. That is, that it can be parsed using a recursive descent parser. That is, that at every choice, we can always make a decision which choice to take based on a single next token. In order to do this, we had some intuition. Now we're working through formalization. There's a lot of notation. It's not very complicated, but there is a lot of it. And so I'm going to review it again, because if you miss one little thing here, like what this individual letter may mean, it will completely throw you off in terms of the overall picture. So let's see what we have here. One thing that we have is this alphas. And any Greek letters, such as an alpha, is a string of arbitrary symbols. So alpha means not a single terminal or non-terminal, but anything, any sequence of them. So alpha, for example, could be A, little a, big B, C, big C, something like that. That's what an alpha is. It's a sequence of arbitrary symbols. Okay. So that's one. We have Latin letters like A, B, C. They stand for terminals. This is something that is a token, something that the lecturer figures out for us. Then we have these capital Latin letters, S and A. They stand for non-terminals. So S is a single non-terminal. A, big A, is a single non-terminal. So in particular, when we look at this string, it basically says it's some kind of prefix alpha, a bunch of symbols, don't know what, doesn't matter what they are, followed by a big A, a non-terminal that is important in this case, followed by little c, which is a terminal, followed by some other suffix. Right? And so if we read the definition of this now, this should make sense. It's a follow of A. So a character, a token that can follow a non-terminal A is what? It's all kind of terminals, such that if we start at the beginning of our grammar, S usually stands for the beginning of a grammar, and we apply a derivation a bunch of times, at least once, then we're able to construct a string like that of terminals and non-terminals. And in this string, there's going to be a big A, which is exactly what follow we're looking for. And after big A, there will be a character C. So follow A is a set of all terminals. I call them characters because we use a single letters, but really they're terminals, they're tokens. So follow A is a set of all tokens such that from a start, we can have a derivation where at some point in the middle of this derivation, we're going to have big A followed by a token C. What else do we have here in terms of notation? I think this covers the big one. So epsilon is an empty string. We've seen that before. Big arrow is a derivation. Big arrow star is 0 or more derivations. Big arrow plus is 1 or more. This is the sets that we care about. Epsilon alpha takes a sequence of terminals and not terminals and tells us whether it's possible to derive an empty string out of them. First of alpha tells us all the terminals from which alpha can start, from which strings that derive alpha can start. Follow A tells us all terminals that can follow A somewhere in the grammar. And then predict of a rule, a non-terminal A goes to a string of terminals and non-terminals alpha. Whether we take this particular choice depends on what is the first of alpha. Now, if alpha is not nullable, then it's easy. It's just the first character, the first terminal of alpha is that's it. That's what determines it. That's most of the examples that we've seen so far. But if alpha happens to be nullable, that is, it's possible to derive an empty string out of alpha, then predict this case also depends on terminals that can follow A. So intuitively, it says we're going to go and do this rule in two cases. One, where alpha we're going to be a bunch of terminals eventually, and we see the first terminal of alpha, and so we know it's alpha. Or case two, alpha could be an empty string, and then we see something that follows A in the grammar, and if something follows A, then we basically assume, oh, it means that we take this rule and also resolve alpha to be an empty string, and that's how we, that's why we're doing that rule. Okay, so that's hopefully you remember from last time. And so we're just going to continue with this. Okay, so we looked at that, just a notation. So we're going to look again at how to determine this predict set. Last time we looked at grammars only with choice. And now what's going to happen is that we're going to look at a grammar with stars. And that's going to be everything that we need. This is the steps that we do, 1 to 5. First, we convert the grammar from its convenient extended form into a simpler, more verbose, less convenient to write, more convenient to reason about, BNF form. Then going to determine what is nullable. Once we know that, we're going to determine the first set for each non-terminal. We're going to determine the follow set for each non-terminal, and using them, we're going to compute predict using the formula that we've seen. Okay? And now once we have a predict, well, we can see if predict sets are disjoint, then the grammar is LL1. And if predict sets are not disjoint, then the grammar is not LL1. Now, of course, we know that just because the grammar is not LL1, it doesn't mean that the language of the grammar cannot be recognized by LL1 by a recursive descent parser. So if we end up with a grammar that is not LL1 for the language which we believe is LL1, well, then we can fix the grammar by refactoring. This is something that we're going to cover after the midterm. If you're interested now, read the notes, lecture notes section for. Now, one other thing that is sort of not on the slide, but now why is this here? Well, once we know our predict sets, we can actually generate the recursive descent parser automatically. If you remember, the way we get a recursive descent parser, we look at the grammar, and we just convert the productions in a grammar one for one into code. We use conditionals for a choice, we use a loop for a star, and then we just write, we use inspect and consume for the other parts. And the only thing that is not completely determined by the grammar trivially is what do we put inside inspect. When we have if, lexer, inspect, what should we inspect in order to pick one or another alternative? And the predict sets is exactly that. So our automatically generated parser will simply say, I look, I have a choice between two rules. I need to know which one to apply. Well, the condition will be is if the next token is in a predict set of the first rule, apply that. And if it's in a second, apply that. This may not be super clear when I say it, but we'll see an example towards the end of an automatically generated recursive descent parser. Okay, so let's look at the example. So say we want to have a language which would be actually before that. So let's just look at there you go. Let's look at this language over here. So for example, we take the language that we had before of strings UW, and now we decide that we'll also allow for an empty string. And the way we do it is we changed A to have another alternative that A can also now be epsilon. So A is either U or epsilon, B is W, and the whole language that we have is A or B. So it's either U or epsilon or W. We need to convert it into BNF form. This is a BNF form. What we do, as you should remember, is we break every choice into individual rules. So now I have two rules for S4, two rules for A instead of the choice. And then I explicitly end of input marker, right? So S4 is A followed by end of input, or S4 is B followed by end of input. A is U, or A is epsilon, and B is W. Now, sometimes when we do this, we can either use this top element, or we can add another non-terminal to represent the top of the grammar. So an alternative would be, we'll say G is S4 followed by end of input, and removes this end of input. And this is important to do if S4 happens to be used recursively inside the grammar. Not here, but just something to keep in mind. And again, we'll see that a bit later on. Okay, so now let's try and do the same thing, but now with this grammar, S5. So this grammar says what? We have an, which is an identifier followed by a semicolon. And the grammar is, and the top rule itself, top non-terminal S5, is n star, right? So what we want to say is that it's either n, or it's 2 n's, or 3 n's, or 4 n's, or empty. And we'd like to convert this without having a star using just the BNF grammar. So here's the trick. So first we're going to do it as a trick, and then we'll think a little bit how to do it. So what the trick is we add a new non-terminal for this whole thing. In this case, I call it list. Also, the name is irrelevant. We then define list to either be nothing, or we define list to be n, followed by list again. Okay? And then n doesn't change. And then where we had an n star, we do a list. Now, if we think about what's going on in this grammar, how acceptance of this will work, how derivations will work. Well, we have a recursion here. We're saying the list is either an end of recursion, it's empty, or a list is an n, and then you recurse, you go back to the top, and then again you have the two choices, either an empty or an n. Okay? So this represents a loop in our grammar, or recursion in our grammar, and that captures exactly what the intention of star is. Okay. I'll let you look at this a little bit, just to see if you sort of follow through, and it does make sense to you. So in order to really understand what's going on, we kind of need to think about how the code corresponding to this grammar looks like, and how recursion in the grammar corresponds to recursion in code, and what this recursion is all about. So let's go and just play with this a little bit. So first, let's look at how this grammar would derive the following input sequence. So we have foo, semicolon, bar, semicolon. Remember, whenever we have a grammar and we have an input string, there's two things that we can do. We can either go from the input string back to the grammar and show how it is derived, or we can start from the grammar and start applying derivations until we derive that string. This is what we're doing here. We're going to go top down, starting from the grammar. We're going to, each time we make a step, we'll do a derivation, which means we pick a non-terminal in a sequence of terminals and non-terminals. We'll pick a rule from here and expand the non-terminal according to the rule. I'm going to use square brackets here all over the place. That will indicate what we did at what time, right? This is just so that we kind of have an intuition of the tree shape of that derivation. They're not part of the strings. They're just there for us to look at. So first we start with S5, and the only rule we have is this one. So we apply this rule, and we get list $. I put list in brackets 1 to show that, okay, this is the first time that list appeared. Keep an eye on that. Next, we need to expand list. We have these two rules to pick out of. I know that I want to derive foo, semicolon, bar, semicolon, so this choice doesn't work for that. So I'm going to pick this choice. I'm going to apply that. I'm going to get this. So here, this list got expanded into n and list using this rule. So now I have the string with two non-terminals, and list. And to do a derivation again, I pick one of them, I pick a rule, and I apply. I have two non-terminals to pick out of. You can pick either one to do first. I'm going to, in this example, pick the list one first. That's because that's what I want to do. Again, I have these two rules to go from. I know that I want both foo and bar to be in my string. So replacing list by epsilon is not the right thing. So I'm going to pick this one. And I expand list2 into n followed by a list. So now you see that my derivation gets me that S5 can derive an n followed by an n followed by a list. I repeat the same thing again. Now I have three non-terminals. I get to decide what to do. And in this one step, I'm applying three rules at once. Otherwise, we don't have enough space on the slide. The rules that I apply is for this non-terminal, I pick this rule, and I get foo semicolon. Now, hopefully you're not confused why this has an ID in it, but this is foo and not ID. Why is that? Well, the reason for this is that the grammar is written relative to our tokens. ID is our token, but when we look at an input string, it's given in terms of the lexemes of the tokens, the values of the tokens, not just the tokens themselves. And so I'm saying and I apply this rule, and I write foo here because I'm assuming that the lexeme of the first ID that I get is foo. I do the same for n for the second n, but this time I use the lexeme of bar. And now I have to do something with the list. Again, I have these two choices, and I would like to not have any more lists. I only have two elements. So I pick this one. I say my list is an empty string. And that's it. Now, if I remove all of my brackets, which were there only for me to keep track of when I applied what, I get a string foo, bar, end of input. So hopefully, this gives you an intuition of how to program in codes using the grammar. We're essentially writing a recursive program where each time we want to repeat something, we just call a non-terminal that has already defined somewhere. Okay. Now, let's go to the next slide. So this is another way to look at this. It's exactly the same thing, just a slightly different interpretation of it. You may really want to think about grammar as a recursive descent parser, really as code. And then to have this connection between the recursion in the grammar and recursion in the code, we can make our code recursive. In your parsers, you were encouraged to use a loop to represent a star, but you don't have to use a loop. You could also use recursion. So this is how the code looks like when it is recursive. Okay? So this is a recursive descent parser for this grammar, and it itself is handling a star recursively. So let's see how it looks like. So the first rule is easy. It's a list followed by end of input. In this case, end of input is end of file. And now we have a list. And what we do for the list is if we happen to have an end of file, we know this is the epsilon case. And so that's it. We're done. We just return. And otherwise, if we know that we didn't hit the end of input case, then we consume an n. And then we call list recursively, which will come here, and it will either say, "Oh, we at an end of input, so the list has to resolve to an empty string," or we're not at the end of input, and then we consume another n and call recursively. And of course, whenever we consume n, what we do is we consume an ID token, and then we consume a semicolon token. So this code really corresponds to this grammar. Like one for one. So there's really like each part of a grammar corresponds to this code. Now you may ask, well, why do we use loops instead of recursion? And there are lots of reasons why in a programming language like Java, loops are preferred. Recursion is, once you understand it and can use it effectively, is a very convenient way to express a lot of interesting algorithms in a way that is very close to their mathematical description. The downside of recursion is that whenever we call functions recursively, we consume stack space. And in most languages, including Java, stack space is limited. Because stack space is limited, much more limited than heap space, it means that if we implement something using recursion, the number of times we can recurse is actually limited, and the limit depends by configuration of a Java parameter, which means when we implement things recursively, there's a limit, in this case, for example, to how long lists we can parse. At some point, we'll hit the fact that we run out of stack space, and the program will terminate with an exception. Whereas if we write it with a loop, where we use maybe a stack data structure on a heap, we can parse as bigger files as the amount of memory that's on our machine. But it's still a useful way to realize and be able to navigate the space that we have grammars. They're more mathematical objects. They're not concerned with how much stack space they take. They're just concerned with the definition, with the equations that define them. And here, recursive equations as a way to represent sequencing. And we can do exactly the same in code. And so if it's easier for you to think about things in code, you can transition from a grammar, think about that it represents this kind of recursive code, think whether it does the right thing or not, then go back to the grammar. But when you implement, you would implement it using, you try to avoid recursion if you can in your implementation. All right. And just to run through this example in case you're still kind of confused about recursion, and we get to use our program understanding skills. Let's build an object diagram for what happens when we parse this example foobar in this. So let's see. So we're interested in what's going to happen once we get to this line 7. So when we got to the end of file. And the claim is that this is how the objects look like at that time. So initially we called S5. We have sort of one variable, one local variable list, and it is initialized to an empty list in the beginning. And then when we right, so in the very beginning, right now it's not pointing to anything because we are right about to call list, and then when list returns, that's what this list will point to. Okay. So then we call a function list. So we are here. We have a local variable n right here. Okay. We are inspecting whether it's an end of file. It's not, because remember our input is foo semicolon bar. So we jump to the else case. We call n to consume n, and we return. We're gonna eventually return this immutable list, but before we do so, we call list recursively. So in the second call to list recursively, let's see what happens before we. Okay, so before we get to this line, we need to process this. So let's see what happens here. We called n. N consumes an ID, which is foo, consumes a semicolon, which is a semicolon, creates a new immutable list, and returns it. So after this point, n points to a new object, which is an immutable list that contains foo and a semicolon in it. We then recursively call lists again. So we go here. We now have a new local variable n for the next level of list. We again get to the else branch, call n again, consume an ID and a semicolon, and create an immutable list with them, which is this. We now get to this point, call list again. This time we hit that it is an end of file. We create an immutable list that is empty, and this is what we are returning, right? So n is not assigned, n is not used in this last iteration of a list, but an empty list is returned. What happens afterwards? So this disappears, and now this empty list is returned in here, and we create a new immutable list, which is a concatenation of the list that n was pointing to and this. So which is essentially is going to be a list containing bar containing an empty list. Right, and then this is returned up, and we create a list containing foo containing bar containing an empty list. Okay. If you don't immediately understand this, work through this example again. It's really important for you to understand how this recursion works and what happens at each recursive call. Especially, well, you need it to understand this material well. You need it for the midterm, and you also need it for the next lab, lab 5 and 6. Once we start using parboiled, you really need to understand what is the execution model of this recursion and how to interact with it. Okay, so we're back from recursion, back into grammars. And so let's go through this example. So we'll have these two examples, one on the left, one on the right. And remember, we're trying to determine which ones are LL1, and we're going to compute our epsilon sets first and follow. So how do we determine epsilon? Some parts are really simple. We just look at each non-terminal, and we look at its right-hand side, and we see whether it's already immediately epsilon, or whether we can see that we can derive epsilon from it. So A, for example, is definitely nullable because it can go to epsilon directly. Okay. B, on the other hand, is obviously not nullable because B always starts with W. Like the only way to derive B is to have a W at the very least. Interesting one is S4. So why is this not nullable? Well, let's see. So for S4 to be nullable, it consists of this string of these two things. A is nullable. Okay? So that means one way to derive S4 is to say A is epsilon. But then if A is null, epsilon, then this thing comes in, end of input, and says, well, then that's what we have to have at the very least. Okay? So S4 is not nullable because no matter what rule we pick, we're always gonna, at the very least, derive a string that contains end of input in it. Okay? So S4 is not nullable. Let's do the same thing for S5. List is easy because we have an epsilon. And is also easy because it starts, there's only one choice for n, and it always includes an ID, so cannot be null. And even if we didn't know what ID is, then we would look at here and we say, well, it definitely has a character semicolon, so definitely not null. For this one, if we wanted to know whether these two things are nullable, now we can say that they aren't because n is not nullable. And so the whole thing cannot be an empty string. And for 5, again, anything that has any kind of token in its rule is not nullable. So it doesn't matter about list, whether it is nullable or not. We just see this, we know immediately S5 is not nullable. So the next thing is we need to determine the first sets for every non-terminal. So let's look around. So for A, we have these two rules. So what can be the first of A? Well, easy. There's only one that works here, this one, and the first of A can be U. First of B, even easier, only one rule. First of B is a W. First of S4. Okay. This is more interesting. So let's see. If we go and take this rule, the second one, then first of S4 is the first symbol of B, and the first symbol of B is W, and B is always W. It's nothing else. So that's easy. So that's one choice. The second choice is this rule. And this one is a little bit harder because the first of S4 is either the first of A, or A is epsilon, and then the first of S4 is whatever is the next after it in this sequence in the rule. And if that is nullable, then it's what's the next one. And if that's nullable, then that's what's the next one, and so on. So here we have first of A, which is U, or A is null, and then the next thing is just one token, end of input. So that's it. And so we end up that first of S4 is UW or end of input. Let's now do this grammar. First of n is easy. It's just an ID. First of list is first of n, which is an ID. And n is not nullable, so we don't need to go further. The second rule is just epsilon, so there's no first. First of S5, well, because list is nullable, we also need to include what follows list. So that's end of input. And then first of list, and first of list is ID. So we get ID. Again, you should be able to, for simple grammars, once you've computed those sets, you should be able to do a sanity check easily and see whether things make sense. So what you expect to be in a first here in all of those sets is that if you see a token from that set and you're doing the production, for the non-terminal that you're doing, then you know in your parser what to do, that it does correspond to some rule. So for example, if we look at S5 and we say, well, why can ID be the first one? Well, we know that ID can be the first one because ece5 can derive a list of ID followed semicolon. And that's an example where the first of ece5 was ID. If we want to know why is end of input a first of ece5, we know that ece5 can derive an empty string. And if it's an empty string, that means that we immediately get to the end of input, and that's it. And so, yeah, so we expect the dollar to be in here, right? And then you go back and do the same thing. You know all your terminals, and if some terminal is not in the list of firsts, you can go and check whether it makes sense. So, for example, for the first of n, there is no end of input. And you know that the only time you will have a first of input as a first of a non-terminal, if that non-terminal can resolve to empty, and n cannot. So that makes sense. All right. Next thing is we need to determine the follow sets. The trick here is to remember that a follow set, we need to look at not the definition of the non-terminal, but where it is used. So where can it appear? And therefore, what other terminal can follow it, or what other token can eventually follow it. Again, we look at this grammar ece4. So let's see. Follow of ece4. That's very easy. ece4 never appears on the right-hand side. So its follow is empty set. There's nothing. Follow of a, again, easy. A only appears in this rule, nowhere else. And the follow of it is end of input. So we got end of input. For B, same thing, only appears in here. The only thing that follows is end of input. Let's look at ece5. ece5 never appears anywhere. Its follow is empty. Now, follow of a list. Again, we see where a list appears. Appears in here. And so the follow of a list is end of input. We also see that list appears in here. Right? Now, it's at the last position, which means whatever can follow list is also whatever can follow the left-hand side. In this case, the left-hand side and the right-hand side are the same. So whatever can follow list is whatever can follow list. So it's list in here. It's end of input. Now, the tricky case, which is follow of n. What can follow n? Again, we don't look at this rule. We only look where n appears. So it appears in here. And so we see that what can follow n is a list. So it could be that it is the first of list. That's what can follow n. But then we need more, because the list itself could also be is nullable. So it could be nothing. And in which case, if this list is mapped to an empty string, then n ends up at the end of this left-hand side, which means whatever can follow n is what can follow the left-hand side. And in this case, what can follow the left-hand side is dollar. Okay? And so we get that what can follow n, it's either a first element of a list, or it whatever can follow a list. Okay? Now, it's super important to realize here that like this follow of list is not because list follows n. It's because list is nullable, and therefore n is at the end of this guy. And therefore, what can follow n is what can follow this guy. In this rule, this left-hand side and the right element of the right-hand side happen to be the same, but they don't have to be. Okay. So now once we have this, we build our predicts. We really only need predicts for whenever we have a choice. So we'll need a predict in here, and we need a predict in here. There's no predict for B. It's a single thing. So there is nothing to predict. Predict for the first rule is a first of A, and because A is nullable, because it can be epsilon, it possibly would follows A. So in this case, we know that we're going to take the first rule if the next token is either U, which is A, or end of input, which basically means that the way we do this derivation is we map A to epsilon, and then we consume end of input. Predict for the second rule is first of B. There's no follow of B because B is not nullable, so we don't need to worry about B being mapped to an empty string, and so we get W. So if we look now at these predict sets for S4, we see that they're disjoint. That's good. That means that so far this grammar looks like LL1. At least whenever we write code for these first two choices, we know what to put in our conditions. If the next token is either U or end of input, then we do this. And if the next token is a W, then we do this. Right? We have the choices at disjoint. Then we have to do predict for A arrow U. That's easy. It's first of U. First of U is just U, and U is not nullable, nothing else. And then predict A arrow epsilon. Well, for that, we need to take a first of epsilon, which is nothing. And then because it's nullable and it's there's nothing else in here, so we need to take the follow of A. And the follow of A is end of input. Right? And again, predict set disjoint. So we know that either the next symbol is U, and in which case we just consume U and we say we found an A, or the next input is end of input, in which case we say we found an A and we don't consume anything. And then the end of input will be consumed as part of S4. Now, we can do the same computation for S5. Here, we only need to worry about this particular two rules, the one that have the same left-hand side. So predict for this is a first of n. There's nothing to follow because n is not nullable, and so this is just an ID. It basically says if we see an ID, then we are in this production. That is, we saw an ID, and then we need to recurse. Maybe there are more IDs, maybe there aren't. And then here for this one, the first of epsilon is nothing. And because the right-hand side is nullable, we need to look at the follow of list. And the follow of list is end of input. And again, this and this are disjoint. So this grammar is LL1. And so finally, I promised to show you, how we can then use this to generate the code for the parser automatically. And this is an example for S4 and S5. You see that whatever is here in blue, this is the only thing that we didn't know how to do automatically before. Right? So whenever you had to do a recursive descent parser so far, you would have the same structure, but somehow you would look at it and somehow scratch your head and come up with what are the right things to inspect in order for this to work. And what we've done today is we've shown that actually it's not, doesn't require some insight or intuition. We can actually have an algorithm that computes this directly from a grammar, and either it's possible, and in which case the grammar is LL1, and we can automatically construct a recursive descent parser, or it is not possible, and the grammar is not LL1, and no amount of you fiddling with this inspects will make it work. And this is what makes it possible for us to generate those grammars, those parsers automatically. This is what we're going to see at lab 5 and 6. So this is what we're going to do next Monday. we'll start using a tool called parboiled, which will automate the parser generation for us. Right? So far, we did it sort of semi-mechanically. We had to take a grammar and write our own code, but most of the code was following a template. And with a parser generator, we can just write our grammar, and the necessary code will be generated for us. There's an advantage. There's less chances that we'll make mistakes, and that particular code can be optimized in all kinds of clever ways. The downside, of course, is that we still want to have our own parser, not just a recognizer, which means we want to build an abstract syntax tree or some kind of data structures when we parse. And if the code is generated fast automatically, we'll have to somehow inject our code into a generated code. And while this is nice on one hand, because we have generated code, less code, fast, right? It will make our debugging and understanding what the program is doing a bit harder, because we'll write code that is not really all of it. It's going to be combined with the generated code and then executed. And we'll never see the generated code because it will only be created at runtime. And so this will create some difficulty that this kind of parser generators are very convenient to use when you have a complicated grammar. They simplify a lot of coding for you, but what they complicate is debugging. And so now that you have the skills to write your own parsers like this, hopefully you will be able to envision how the code is actually executing. And then through that, you'll be able to debug it effectively. Okay, let's see. That's almost all the slides I have. So there's one extra slide. I'm not going to go over it. It's really too small to see like this, but you can zoom in. It's in a PDF. This just summarizes everything that I've done on slides in one algorithm of how to compute first and follow and predict sets. And so I'm going to pause for questions to see if there's any. And if not, I'm just going to go through one more grammar that's a little bit more complicated than we have on the slides. And we'll try and work through it and see if it's LL1 or not. So let me know when we are in sync. Either ask a question or at least say that we've synchronized and you're ready to continue. All right, so we're in sync and there are no questions. So let's go. This material is not very hard, and I can see why there wouldn't be really questions, but it is tricky. So it's useful to do a few examples and see what to do with the tricky cases. So I've created this language, and so we're going to go through a bunch of steps here. So the language is of letters. The alphabet that I have here is A, B, C. And I've written this language in the set notation, the set comprehension notation. So it says, I either have strings that have A's and B's in it. A's come first, B comes second. Number of A's can be any amount, even 0. The number of B's can be any amount, but at least 1. Or I'm happy with a string that contains only C's, no A's and B's, and the number of C's can be any amount, even 0. So the first question is for this language, whether this language LL1. So let's see, is this language LL1? So let's see if somebody can answer that. If you don't know, just say, I don't know, so that I know we're in sync and you just want me to give you an answer. It's kind of a trick question. We actually know the answer, but maybe this wasn't super clear. So this language is definitely a regular language. And I know it is regular how? So is this language regular? Remember, regular means that we can recognize it by a finite automaton. And there's two things that we know how to show that the language is regular. One is create a finite automaton that accepts it. Two, create a regular expression that corresponds to it. So is this language regular? Again, if you don't know, just say don't know. Okay, so somebody says it is regular, and so how do you know that it's regular? So, yep, it is. Right? So one way is to show a regular expression, and a regular expression could be a star, B plus, or C star. Right? So number of A's can be any, including 0. Numbers of B's is at least 1, or it's only C's and a whole bunch of them. Okay? So the language is regular because it corresponds to this regular expression. And now, do we know is this language LL1 or not? Well, we actually do. It is also LL1 because we know that every language that's LL1 is a language that can be recognized by a deterministic pushdown automaton. And of course, just because I have a stack, I don't have to use it. So any language that is regular and is recognized by a finite automaton without a stack is also LL1 because it can also be recognized by an automaton that is allowed to use a stack. So we know that regular languages as a subset of LL1 languages. And this is in the lecture notes. We have talked about this a bit, but maybe it wasn't stressed enough. So one way to show that the language is LL1 is to show that it is regular, even easier, and therefore we know that it is LL1. Now, it doesn't mean that a grammar that we can write for this language is always LL1, right? Because we can have a grammar that is not LL1, even for a language that is LL1. But let's try and create a grammar for it. So the grammar for this language, one way to do it is we can just say, okay, it's S. And for regular languages, it's really easy. Just the regular expression itself is EBNF almost. So A star, B star, or C star. That's my grammar. Okay. I'm using the trick that B plus is the same as B followed by B star because I don't have plus in my EBNF. Again, I can add it just as a syntactic sugar like that. So that's my grammar corresponding to exactly the same language as a regular expression. So now the next step before I can go further is this is EBNF. I want to convert this grammar to BNF. Okay, so how would I do this? Well, I need to break my disjunction into two rules, and I need to deal with stars. So let's see. So first, let's factor out let's do it this way. So I'm going to factor out the stars. Okay. So what I'm doing here is I'm saying I'm going to have a non-terminal A, which will correspond to A star, a non-terminal B that corresponds to B star, a non-terminal C that will correspond to C star, and S is one of those two things. And then for each star, I'm going to have that say A goes to epsilon, and also A goes to little a, followed by big A. B goes to epsilon, B goes to little b, followed by big B, C goes to epsilon, C goes to little c, followed by big C. Okay. Again, you look at the grammars, if you look at the lecture notes, you'll see I'm using the same pattern there. And if you just look at the grammar, you should be able to say, oh yeah, so A is either empty or it's little a followed by big A, which means either empty or little a followed by big A, and so on and so on. Right? So we recursively get a whole bunch of A's, a whole bunch of B's, and a whole bunch of C's. Now I need to do one more thing, and just to make my life super easy, I'm gonna add an extra top G. And I'm going to say it's an S followed by end of input. Okay. If S doesn't appear on the right-hand side, you can just add end of input to the end of S. But if S does appear somewhere on the right-hand side, that will not be correct. And you do need to introduce a special extra non-terminal for the top of the grammar. And for me, it's easier to always do this, and I know that I'm not going to run into mistakes like that. The downside is that I have one more non-terminal, so I have one more thing for epsilon, one more thing for all the other sets. But this is now a grammar in BNF. And again, we can do sanity checks to see whether that accepts what we want. So we have two choices, so either C or S. C is definitely C star. It's either an epsilon or it's a bunch of C's. And then the other choice is A, which is A star followed by little b, followed by B star. Yeah, that seems to be the right language. So now we start now we need to decide whether this is in fact LL1, the grammar, not the language we already know. And so let's start computing our sets. So let's see, let me try and put some of the sets on the side, otherwise not everything will fit. And let me maybe use a different color. Okay, so what is the epsilon? So I have G, S, A, B, C. Okay. So what is their epsilon? So for G, it is not nullable because G includes end of input as part of it. For S, well, this is tricky, so let's leave S alone for now. A is nullable because it can be an epsilon, B is nullable, C is nullable. So now let's go back to S. In the first rule, S is not nullable because even so A is nullable, B isn't. So the first rule includes at least one B. The second rule, it is nullable because C is nullable. And so we can go from S to C to this rule and we'll get an epsilon, right? So we can get a derivation C goes to S, goes to epsilon. So S is nullable. So next we need to compute first and follow. So let's do first. So first of A is just A. First of B is B. First of C, big C, is C. This is the easy cases. Now, first of G, again, that's also the easy case, is first of S together with end of input. Why? Because S is nullable. We know that from here. And so we have to consider that it never happened. And then end of input is the only thing that we see. And that's the first of G. And first of S we need to compute in order to know what the rest is in there. So let's see what is first of S. Well, it's either first of A. So that's A. But A can be nullable, can be null. So then it's the first of the next one, which is B. B cannot be nullable, so we don't need to consider more. That's it. And then from the second rule, it could be first of C. And first of C is C. So this is A, B, C. And now we can update this guy. It's now A, B, C. End of input. Okay. So again, we can do some sanity checks to see if this is okay. So what is the first of S is basically the first character, the first token with which our language can start. And we're saying, well, it's either A, B, or C. And yeah, that's the only things our language can start with. First of G is, in addition, includes an end of input, because if our language includes an empty string, it starts with nothing. So S starts with nothing, and then end of input is the first symbol of G. Otherwise, it's the first of S. And then for A, B, C, we're done. So next, we need to compute the follow sets. So let's see what is if. Let's compute the follow sets. So let me rearrange things again so that we have something visible. So let me move this here. And we'll do the follow sets. So follow of A. Let's see. Well, we need to remember where A happens to appear. So A appears here. And because it is the last element, so follow of A is also follow of this left-hand side, which is follow of A. Okay, so that doesn't get us anything new. We have to look at other rules where A appears on the right-hand side. Here's one. Yeah, let me use a different color. Here's one here. And so what follows A in this rule is B. So one follow of A is B. A doesn't appear anywhere else. So that's it. That's we done. What can follow B? Again, we have the cycle in here, so that doesn't give us anywhere. And then B can be here. It can be at the end of S. And because it's at the end of S, we need to go and see what can follow S. Well, S only appears in here, so end of input. So that's follow of B. And follow of C, again, the cycle gives us nothing. C appears at the end of S, and we already know this. Follow of S, we already know it's just end of input. And follow of G is nothing, because G is the top rule. Nothing follows it. All right. And so finally, we're ready to compute our predict sets. So what predict sets do we need? Well, every time where we have more than one rule with the same left-hand side. So we'll need a predict here, 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 and here. Right? For each one, we'll need to do a predict. So let me Yeah, I don't necessarily want to do all of them here because it's going to be too messy, but let's see. So let's do predict of A goes to AA. And so this is going to be first of AA. And we don't include a follow because AA is not nullable. And so this is going to be just A. And then we need to do predict of A goes to epsilon. And so this is going to be first of epsilon. And because epsilon is nullable, it's going to be union with follow of A. The first of epsilon is empty, so that goes away. And follow of A, we know it's B. So move this here. Okay. So we know that the predict sets, at least for this rule, are disjoint. So let me just annotate them here. So I'm going to put the predict set on a rule so that we know. So the symbol on top of an arrow, it means that if we inspect and we see the next token is A, then we take this rule. And if the next token is B, we take this rule. So then next we need to do predict for B goes to BB. This is going to be little b. And predict B goes to epsilon will be follow of B, which is end of input. B, end of input. Again, the predict sets for these two rules are disjoint, so I know which one to apply. And we'll do predict C goes to CC. This is C. Predict C goes to epsilon, which is follow of C, which is end of input because of this. So end of input, and this is little c. Okay. So again, you should be able to do a spot check. It's a small grammar. So here we, okay, I mean, these parts are very simple. The first part of the right-hand side is a non-terminal. This part, ouch, this part. So A is empty. It has to be followed by B. And we know that our language, if it has an A, then eventually we see at least one B. So the only way we can say no more A's is if we see a B. So that's correct. And then whenever we see either B or a C, we're going to keep seeing B's and C's until end of input. So that's why these are correct. But this was just my sanity check, spot check. So just using my intuition to see. And so now finally we have the S things. Okay, so let's do that. So predict S goes to A, B, B. And this is going to be first of A, B, B. It's not nullable, so there's no follow. And first of A, B, B is going to be first of A together with B because A is nullable. And first of A is, well, let's look it up. First of A. First of A is A. So this was B. And this is A union B. Okay. And to clean it up, so it's AB. is what I want. And then predict S arrow C. So this is going to be first of C. But because C is nullable, together with follow of S. First of C is just C. Follow of S is end of input. And so I get C end of input. Let me go back. Let's remember what we have here. So AB is first and C dollar is second. So let's annotate them here. So A comma B. And C comma dollar. Okay. And that's it. I don't need to do any more. I don't need to do this rule because there's only one of it. So there's no choice. And so what is this telling me? It's telling me that I can construct my recursive descent parser for this language. And the way it will be, in the code for S, which is here, I first inspect whether the next symbol is A or B. If it is, then I expect a big A followed by B followed by big B. And if it's C or a dollar, then I know I'm expecting a C. Okay, so an empty string is parsed kind of as a C, and a string that starts with either A or B is parsed using the first rule. And strings that starts with a C is parsed using the second rule as well. Right? That's it. So all of my choices are disjoint. There's no thing that I can do using two rules, and there's no ambiguity. And so therefore, this grammar is LL1. And that's it. Well, if you have questions, ask them now. If you want me to post the PDF of what I've just done, ask, I will. But it is on the video, and it's probably more convenient to look at it on the video as I do it, as opposed to the PDF. But I'm happy to upload this one as well. We'll have one more tutorial, not this week, obviously, but next one. And this will be a tutorial on LL1 where ATA will do a similar thing with a different grammar. So it will give you more time to practice. All right. So thank you very much. I don't see any questions. Good luck with Lab 4. See you back on Monday. I will try to announce the lecture before, but even if I don't announce the lecture, it's gonna happen Monday morning, 10 a.m. So don't forget about it. Yep. I'll see you again on Monday. Have a good weekend.